In this video, I'm going to talk about simple harmonic motion. I'm going to talk about what it is, the conditions needed for something to undergo simple harmonic motion, and a couple examples. Please read the success criteria of what I'm going to cover in this video. Here are a couple of examples of things that would undergo simple harmonic motion. So first of all, here I have a U-tube. No, this kind of U-tube. It's just the shape of a U. Now, if I just leave water in my U-tube, it would be balanced like this, and water would be the same height on each side because they're both open to the environment. But if I pushed this side down, since water is not compressible, this side would go up. And once I stop that, it's going to go back and forth and back and forth. And that would be simple harmonic motion. It's a periodic to and fro motion. I have here a parabola. So let's say I put a ball right here. And if I let go, it's going to slide down. It's going to get to the bottom, and it's going to come up the other side. And assuming there's no friction, it's going to go up to this height, and then back down, and back and forth with simple harmonic motion. Now, what I have here is I have a torsion pendulum. And let's say I take this and I rotate it. Not swinging back and forth, but I just twist it a little bit. It would, in this case, go counterclockwise, get to a maximum, and then come back clockwise, and back and forth. I'll have a periodic motion as my object moves. So here's another example of something that does simple harmonic motion. And a pendulum will do this as long as we use small angles. If you have something more than 5 degrees, or I'd say in practicality in a science lab 15 degrees, then it will undergo simple harmonic motion. But if you take the pendulum and you go way out here, then it's actually not going to meet all of our conditions that I'm going to keep talking about. So first of all, let's talk about the word oscillation. If I pull my pendulum here and I'm going to start at A, I would have to, for one oscillation, go all the way from A, B, C, D, E, and back again until A for me to have one oscillation. Now notice, I don't have to start at A. I could have said from E to A and back, or I could have said C, B, A, B, C, but notice now when I get to C, I'm going in the opposite direction I started with. I'd have to go back up to E and then back down to C. So I return to the place I started and moving in the same direction. For a period, that's going to be the time it takes to complete one oscillation. Frequency will be the number of oscillations per second. We have for period, we use the letter capital T, and for frequency, it's a little f. Now, time it takes for one oscillation compared to the number of oscillations per second, they're actually inverses of each other. So we get the equation T equals 1 over f. Now the angular frequency is going to be given the letter omega, and omega is going to be 2 pi f. This is going to be then the number of radians per second. I could also write this equation as omega is 2 pi over t using this equation here. Two more words I want to include before we move on is that we're going to have a displacement. We're just like in math class, and we have a number line. And your math teacher says going over here to the right will be a positive for your number line, and the left would be negative. We're going to say C is our equilibrium position. In other words, where is my object when it's not undergoing simple harmonic motion? Where is its resting place? Now, displacement, if you remember, is distance that's a vector, so I need a direction. So in this case, my displacement would be positive, and we would say this direction, or this distance here, x. So for A, I have a displacement of positive x, where E has a negative x. And the restoring force, if you think about this, our pendulum, if I let go at A, why does it move? Well, there must be a force pulling it towards the equilibrium position. Once I go past the equilibrium position, and now I'm moving on towards D, now my restoring force is actually going to be pushing it backwards. It wants to make it stay at the equilibrium position. So as I go from A to C, my restoring force is pushing to the left. Once I pass C over here, now my restoring force is going to be pushing me to the right. So now you can see that we have a restoring force that's always trying to push the object back towards the center. And a key requirement or condition for simple harmonic motion is the farther from the equilibrium, the greater the force. Note that means that the displacement and the force are always in opposite directions. When I had my pendulum over here, I said my force was to the left, but my displacement was to the right. When I got over to this side, now my displacement was negative, but my force is to the right, which is positive. And for simple harmonic motion, these two things must be directly proportional. That means my restoring force is going to be proportional to x. But I need to put a negative sign here because these are both vectors and they are in opposite directions. We can also write this as A is proportional to negative x because we know, as I've written here, force equals mass times acceleration. And so force and acceleration are also directly proportional. I could substitute this in. But beware, this is not a constant force. This is one of the examples we have in the syllabus that is a non-uniform acceleration or non-uniform force. That means you cannot use velocity as distance over time, which is only for constant speeds, or acceleration is v minus u over t, or any of those Suvat equations. They cannot be used. And in another video, I'll go through the equations we can use for simple harmonic motion. So, is this an example of simple harmonic motion? I've got a picture here of somebody jumping on a trampoline. Now remember I said the condition, we need to have f is proportional to negative x. So when the kid is on the trampoline and they're landed and they're moving down, they're moving in a negative direction and the net force is upwards. Now it does work that the forces and the equilibrium and the displacement are in opposite directions. But do we have that the force is proportional to the displacement? On the bottom, the farther I go down, the bigger the force of the trampoline is going to push me up. But when I'm on the top, when I'm not in contact with the trampoline, the only force I have is the force due to gravity. And in this case, since the force due to gravity is constant, it is not proportional to how far away I am from the equilibrium position, and this is not simple harmonic motion. Even though there might be a periodic motion, maybe I do have a restoring force towards the center, I do not get this relationship, and it is not simple harmonic motion. Example 2. We have an object undergoing simple harmonic motion about a point P. We don't know if it's a U-tube or a torsion pendulum, It says its magnitude of the displacement is x. Which of the following is true? The direction always has to be towards the center, so this is not going to be true. It's always a restoring force. And is that restoring force proportional or inversely proportional? We know that's proportional. That means the only possible answer is A. Okay, example 3. I've got a small little ball here on a curved track, and it's pulled to the side this distance x and released. And it tells me that the expression of the acceleration compared to its displacement is given by this expression. And it says, show that the ball undergoes simple harmonic motion. Well, remember, for simple harmonic motion, our acceleration has to be proportional to negative x. If you take a look, I've got A equals, now I've got this g over r times x. Now g and r are constant. And that means I do have my appropriate relationship. Notice that I'd get 1 mark for actually saying what the relationship I need is, and the second mark would be saying that g and r are constant. If you don't point that out, there's no reason to assume this equation would give this relationship. And finally, please read the success criteria 1 more time. I hope that after watching this video, you can say yes to all these pieces.